Hello, this is Ian Woolf. While I take a break, listen to Diffusion Science Radio from the 15th of August, 2010.
Diffusion, the international science radio show.
We have a bouncer on the doors of perception.
The good, the bad, the ugly.
It gets pretty exciting.
The myths, the truths.
Toxicology.
Astroseismology.
Magnetism. The dark side.
Genetically engineered potatoes.
Planetoid.
Planetoid.
I love that word.
Greetings and welcome to Diffusion Science Radio, coming to you from the Ultimo Science Festival during Science Week here in Australia. I'm your host, Marc West, and this week we're talking your science questions. Over the last month or so, we have asked you to send in your burning science questions, and you have done so via Twitter, email, Facebook, and face-to-face. I'm here with Ian Woolf and Victoria Bond. Let's get to it. And the first lot of scientific facts that we're going to tackle today are the physics questions. Ian, you are our local physics expert. What questions came in?
Well, a big thank you to Ian Roberts in Sydney, who asked, what do I see if something is coming at me at the speed of light? Now, this of course goes directly to Einstein's mind experiments with relativity that led him to develop his theory. He imagined, what would you see if you were travelling with something that's going at the speed of light? What would you see? And the answer is, if something is coming right at you, if you're standing still and something is coming right at you at the speed of light, you can't see anything because the light that carries the information that the object is coming right at you is travelling at the same speed as the object itself, and so you don't see it until it hits you, by which it's too late. So you can't see it at all. It's not black, it's just not there until it's too late.
So it could be a little flash at the rods and cones at the back of your eye, perhaps.
Well, from what? If you're seeing something from the side that's travelling that fast, maybe there's a vector that you could see a little bit that was travelling something.
Well, that could be really interesting because light travels at the speed of light, no matter what direction it's going. The vector diagram. I'm not even sure how that would work. Very relativity.
And then, of course, there's things travelling at the speed of light or even faster than the speed of light in a medium. You can travel faster than the speed of light in a gas or a liquid, but just not faster than the speed of light in a vacuum.
No, yeah, you can't go faster than C.
That's
3
right.
times 10 to the 8 metres a second.
Speed of light
roughly
in
that,
a vacuum. But in a gas or in water, you can go faster than light. Still less than C, but faster than light in that medium. And in which case, if you have, say, a radioactive particle that goes off, a little electron goes off faster than the speed of light in water, then it glows blue with Cherenkov radiation.
Why is it blue?
It's because it's high-frequency light. It's going very fast. It's high-frequency light. It's a big lot of energy that's going out. I mean, there'll also be X-rays, but blue is what you can see.
Right. Oh, okay. So blue's sort of the tail of the...
The tail of the nasty
that
stuff
curve,
coming
yeah.
out, which is why radioactive things glow in the visible spectrum at all.
Okay. Interesting. So there, the answer to that question is, well, you wouldn't see anything.
You wouldn't see anything until it hit you.
Righto.
Again, things coming right at you. If you shot a bullet with a given velocity and mass from a room at 298 Kelvin, which for those of you in Celsius is 25 degrees, into a room at 0 degrees Kelvin, which is as cold as you can get, what would happen to its momentum and trajectory? Now, this is a thermodynamics question because 0 degrees Kelvin is one of those things that you can't actually quite reach in the real world. It's no ideal situation. And in thermodynamics, movement of particles is what is considered heat. And so there's conduction of that little movement is how heat conducts from one particle to the next. So if a bullet is in a room at 0 degrees Kelvin, the bullet will be hotter than 0 degrees Kelvin, quite a bit hotter. So if you shoot into that room, the bullet's just going to keep on going. It won't be stopped, it won't be slowed. If you insisted on the bullet being at 0 degrees Kelvin, then you get into definitions of movement and heat.
Of what temperature actually is, I guess.
That's right. And the last question from Balthazar Lechen. When astronomers take pictures of space, the information they get has a very wide time span. Some of the light comes from a few light years away, and some can come from 1,000,000 light years away. Therefore, the information they have is not true, by which I think he means it's not the current up-to-date information, it's old. Since a star that appears to be at a particular spot could be somewhere else completely different or may have actually died and not exist anymore. And this is true for a lot of stars. So how's this taken into account when trying to analyse the universe? Now this is a good question because the universe is pretty big. Now our galaxy is 100 million light years across. So stars from the furthest end take 100 million years for the light to get here and tell us. But stars are very long-lived, so in 100 million years, not very much happens. It's unlikely that it's going to be dying. Most of the stars aren't in that stage, so the star's probably still around. Will it be in exactly the same place as we see it? Well, we can predict where it's likely to be over that period of time, so we can take that into account. You can build computer models. But all we have is what we see plus mathematics, and when you put those two together and you get a computer model, which is how they determine the large-scale structure of the universe, which spans many more millions of light years than just merely 100.
The next question we're going to answer today is the question, why do I sneeze at the sun? From Lisa Bailey in Adelaide. And I actually also suffer from this affliction, or whether or not it's an affliction, well, that's for us to find out right now. It's actually called photic sneezing. And I spoke to Professor Louis Partek from the Howard Hughes Medical Institute, who studies neurogenetics. And the first thing I asked him was, is it real?
It's absolutely real, and it's a phenomenon where people, after being in relative darkness for a certain amount of time, walking out into bright light or turning on a bright light will lead them to sneeze usually the same number of times each time they go through that cycle, and it may be once or twice or three times or more. And we really don't understand why it happens, but there's no question that it's a real phenomenon, and it appears to affect perhaps as many as 10% of the population. And it appears that it's a genetic trait that's passed on from people who have it to 50% of their children on average.
Okay, and it's always a multiple sneeze, is it? So it's not like, well, is it in any way related to, hay fever or smelling pollen, that sort of thing?
Oh, no, completely different.
What sort of purpose would sneezing at the sun cause? Is it something that we've evolved to do, or do you think it's a byproduct of something else?
I can't say with any certainty since we don't understand what it is precisely. I can't think of a selective advantage of sneezing when you go from dark to light. But I also can't think of a selective disadvantage, again, unless you were flying an airplane at a Mach 1 and the light coming through the trees led you to sneeze and you tipped the controls and crashed.
Yeah.
But I can't think of any example where sneezing in that setting would actually help you. When you sneeze from a cold or hay fever or dust in the air, that's really more of a protective response. You may have inhaled some pollen or dust that's irritating the inside of your nose or your airways, your upper airways, and so a sneeze often allows you to just blow all that stuff out, clean out some of the stuff that you may have inhaled that is causing some discomfort for your nasal mucosa.
And is it associated with age or sex? I know it's genetic, so if your parents have got it, you've got a higher chance of getting it, but is it associated with any other factors?
Not that we know of. I should emphasize again, we know very, very little about it, except that it exists. Because it's not a disease, if people were dying from this, then, of course, we would know a lot more about it because a lot of people would study it. But it doesn't seem to be a good thing or a bad thing. It just happens that about 10% of the population do it. And it appears to come on, again, nobody's looked in a really careful way at this, but my impression from talking to lots of people with photic sneeze reflex is that it comes on in childhood and often is lifelong.
It's really interesting the mechanism that must bring on PSR, because normal sneezers the stimulus comes in through your nose, but in PSR the stimulus comes in through your eyes. I think I read somewhere that there's a theory that maybe there's some short circuit going on in your brain with the optic nerve triggering the sneeze response. Is that possible? It kind of sounds speculative.
Oh, it's completely speculative. It makes sense at an intuitive level. Let me go back to something you said before. It's not that the muscle takes time to relax. When you sneeze, that's a acute and very organized contraction of the diaphragm muscle, and it relaxes very quickly. So I think whatever it is about PSR has something to do with a refractory period in either photoreceptors in the eye or some, a refractory period of some a group of neurons in the brain that are responsible for this circuit. Yeah, so intuitively it makes sense that if, for example, the nerve that makes your eye, the hole letting light into your eye gets smaller when you walk into bright light, that happens, right? If you shine bright light in someone's eyes, the colored part of their eye gets bigger and the black hole in the middle gets smaller.
Yeah.
Because of the contraction of that muscle or relaxation of that muscle, I don't recall which. If, for example, nerve fibers from that should have gone to the eye, in fact, were going to the diaphragm, that would make sense, right? That you activate those just in the same way that you activate the nerves that are making your eyes the hole in your eyes get smaller, so that it protects your eyes from getting too much light. But I don't think that there really are nerves that are going all the way from the eye where they should be down to the diaphragm.
Yeah, that's a long nerve.
But rather, it could be some short circuit or an abnormal connection somewhere in the brain or brain stem. That seems perfectly plausible and intuitively pleasing as an explanation. But there's zero data in support of that, and zero data refuting that. I simply can't say anything other than, yeah, that sounds sort of like an attractive idea, but we simply don't know is the bottom line.
So, guys, I sneeze at the sun. I am a sufferer of photic sneezing. How about you?
No.
No? Victoria?
No, I don't sneeze. It'd be interesting to have our listeners actually, answer a poll or something so we could get larger numbers and maybe statistical power.
Well, I've actually started up a poll and we'll put it up on the Diffusion Facebook page.
Fantastic.
And everyone can participate. Our Facebook page, if you don't know, is facebook.com/Diffusion Science Radio. So get over there and become a fan of Diffusion. But yeah, I have suffered this for all my life. Both my parents have it and my brother has it. So it's definitely a real thing, but people used to laugh at me when I said it, but it's completely real.
And so you were saying earlier, do you think it might be dominant?
It's definitely genetic. Yeah.
It's definitely genetic.
Yeah, but I can't think of any evolutionary advantage you would have with it. But then I guess if there's no disadvantage, there's no pressure to get rid of it, to select it out. So it could just exist through genetic drift, I guess.
Or it could be tied up to something that is useful, because genetics are like that.
Yeah. Interesting to know what it is. Don't know what that is. This is ongoing research. Victoria.
Next up, I took a question from Anka Arnhem, who asked a question about the physiology of fat cells. I managed to corner Dr. Bernard Champion at Nepean Hospital. If cells in our body are replaced all the time, and nothing in our bodies is as old as we are, will superfluous fat cells disappear when you slim down, or just be replaced by new ones? I've heard many times that even if you lose weight, you will put it on really easily again, because your fat cells just fill up if you even think about eating a piece of cake.
It's a good question. It's a difficult question because we probably don't know the exact answer. What we do know is that a lot of people can lose weight, but only around 10% of people who lose significant amounts of weight, and by that I mean maybe more than 5% of total body weight, actually maintain that weight loss long term. And there seems to be almost an energy homeostasis back towards whatever weight you've reached or plateaued at. When they have studied these people who've lost that weight, so say they were 100 kilograms, or say they're 110 kilograms and they lose 20 kilograms to 90 kilograms. When they've done studies of their fat cells, usually subcutaneous, and there's different types of fat. You have to understand there is bone marrow fat, there is visceral fat, and there is subcutaneous fat. it's relatively easy to study the quantities of it through CT, ultrasound, DEXA, densitometry imaging. It's not so easy to study what's actually happening at the actual cellular level. What we do know is that when you take biopsies from those people who've lost significant weight, when they get fat, when people put on weight, the fat cells get both bigger and more numerous. So they get there's hyperplasia of fat cells, and also, I suppose you could say hypertrophy, but bigger and more of them. Sadly, it seems to be when we lose weight that they don't die as such. They just get smaller. So we have a lot of small fat cells. And yes, the theory is that at each new level of weight, you've got an increased number of fat cells that if you then create the energy conditions in terms of intake and expect, like you were doing a lot of exercise and you've cut back on that those fat cells that have been a little bit inert but not dead are sitting there ready to take up whatever energy they can gobble up and reaccumulate fat and size and put weight back on. It's actually very complex in that the other thing we do know is that we used to think fat was just fat as storage, energy storage vehicle. We now know it's actually a gland. It's very hormonal. It's arguably the most hormonally active tissue in the body. And it secretes hormones called adipokines. And if you look at obesity and diabetes or diabetes associated with weight gain as an inflammatory condition, when people put on weight, there is a whole series of derangements in these adipokines. And even though a lot of them are made by fat cells, the good ones that are insulin sensitizing and help with appetite satiety tend to go down or show resistance phenomena, and the bad ones tend to go up. And so, again, in these weight loss conditions, there are changes in some of these hormones, and these are things like adiponectin and resistin and leptin, and there's even roles for interleukins in this. Ghrelin's another one, but there are imbalances in the overweight state and the weight loss state that maybe conspire against us to
actually keep the weight off. Yeah.
The final thing I'll say on a positive note is there's a special registry in the US, and I've forgotten the name, but it's a self-reported weight registry. And to qualify for it, you have to have lost a certain amount of weight for a certain period of time. And it's something like at least 10 kilograms for at least 2 years. And when they've done it, and there's quite a big registry, I've forgotten the numbers, but there's 500,000 people on it or 2 million people on it. When they analyse what the people who really have lost weight and kept it off have done, there's fairly common things. They're really strict with their eating. They weigh themselves regularly, at least a couple of times a week. They do regular exercise, approximately 60 minutes a day of brisk walking, okay, which you can cut down by doing more vigorous exercise to probably half that time. They act quickly on small changes, so if they find themselves going up 2 or 3 kilograms, and this gets back to your listener's original question, but they tend to act on small weight fluctuations to try and stop them. And so there was several of these sort of markers, but they reduce fat in their diet, they reduce portion sizes.
Dr. Champion, thank you very much.
You're welcome.
So in summary, if you put on weight, you put on fat cells, but when you lose the weight, you don't lose the fat cells. There is an uplifting story for you. And from one uplifting story to another, I had a question from Andrew Mosey in Sydney, who asked, why do sportsmen train at altitude? So I took this question to Professor Chris Gore, Head of Physiology at the Australian Institute of Sport. Here's what he had to say.
I guess step one is to define the sort of altitude that we're talking about. And a lot of people think of altitude, you think about going up a mountain to substantial heights and, climbing peaks and everything else. But for athletes, effective altitude is probably in the range to 2,000 to 3,000 metres altitude only. Give you a perspective on that, Kosciuszko's 2,228. That's our highest altitude in Australia. And so we usually have to go overseas to get to the sort of altitude that athletes like to train at.
And so an athlete performing at a very high altitude, well, above 2K,
Yep.
What are some of the things that happen? I know we all know about altitude sickness, but what are some of the other things that can happen to a body?
Well, just for clarity, then altitude sickness is induced by ventilation, so how much you breathe or lack of breathing to altitude. You get things like a minor headache just once you get over 3,000 metres. But for most athletes at 2,000, 2,500 metres, those ventilatory changes still happen, just to a more moderate extent. Probably the first thing that most people think about is making more red blood cells. You go up altitude a little bit, your body senses that there's a lower level of oxygen in the kidneys, and then the body signals the process to increase the rate of production of red blood cells.
Okay.
And that's a very, very common, strong understanding about what altitude is all about. We at the AIS have done a fair bit of research looking at other areas that are related to red blood cells, but also not related to red blood cells. And things we've looked at is one thing called muscle buffer capacity, and that's to do with how the body handles, say, lactic acid, lactate, and found some very positive benefits from athletes spending time in simulated altitude of 2,500 to 3,000 metres in terms of how their body is more effective, I guess, at handling blood lactate.
And so this is not so much due to is it a lack of oxygen, or is it due to there's the pressure of oxygen is just less up there, isn't it?
Yeah, very, very correct. The amount of oxygen, roughly 21%, is the same, once, even at the top of Everest, it's still 21%. The difference is the pressure. So when you're flying in a plane, a commercial plane, across to Sydney or, Perth or whatever, when you hear it popping, that's the changes of pressures, just like if you drive up a decent-sized hill. It happens about every 300 to 600 metres, depending on the individual. It's the changes of pressure, and that change of pressure means that the availability of oxygen across the lung is different. You can imagine there's the pressure helping to force or the diffusion of oxygen across the lung. If you reduce the driving pressure by being higher at altitude, it's harder to get oxygen across the lungs.
And how long does it take to adjust at, let's say, an altitude of 2.5K, say? How long does it take to physiologically adjust to that? Can you ever adjust as well as somebody who's born there and lives their life there?
Yeah, I think that at those sort of altitudes, the probable answer is yes. You can probably adapt mostly in a couple of weeks. To be able to perform quite well if you're an athlete. I've got good colleagues over in Colorado Springs there who measure military cadets at around 2,200 metres, and they look at the time course of their hemoglobin and other changes in the body over a year or more, or 2 or 3 years of our cadets, and find that in terms of the red cell changes, it probably takes up to 6-8 months until they get full acclimatisation at that sort of altitude.
Wow, 8 months.
Mm-hmm. That's for the red cells. But, if you can imagine, it's like an asymptotic curve where it sort of goes up quite rapidly and then plateaus off sort of gradually reaching the new plateau. But for athletes wanting to go and compete at, 2,500 metres altitude in some sort of endurance event, if you spent a couple of weeks at that altitude, which is what a lot of people did before Mexico Games, it's a pretty time-efficient way, I guess, of getting most of those adaptations happening in the body.
You're listening to Diffusion Science Radio across Sydney on 2SCR, across Australia on the Community Radio Network, and across the world on the podcast. And that's all we have in this week's edition, this Science Week edition, of the Diffusion Science Radio Show. We only got to a few of your questions today, so listen in over the next few weeks as we tackle some more of them. And we'll also play longer versions of the interviews you heard today. And remember to get over to the website www.diffusionradio.com for some notes on these questions, and also some notes on some questions that didn't get to air. Also remember to get over to our Facebook page, facebook.com/Diffusion Science Radio, to participate in our sneeze survey. Do you sneeze when you look at the sun? Diffusion was produced today by myself, Marc West. Joining me on the program were Victoria Bond and Ian Woolf. We will broadcast across Australia on the Community Radio Network.
Diffusion is syndicated globally on the National Science Foundation's Science 360 internet radio station and also on astronomy.fm.
Or perhaps you listen to us on your podcasting device of choice. If you'd like to subscribe to the podcast, get over to our website, www.diffusionradio.com. If you've got any burning science questions, why don't you email them to us at
science@diffusionradio.com.
My name's Marc West. We'll catch you next week on the Diffusion Science Radio Show.
It has to